Two particles can be born in the same quantum event, fly to opposite sides of the galaxy, and still behave as if they share a single, indivisible coin flip. Change something about one, and the other responds instantly, even though nothing travels between them fast enough to explain it. This is quantum entanglement, a correlation between particles so strong that their properties cannot be described independently. To see why this is weird, we need to recall how quantum particles carry information. An electron, for example, has a property called spin, which you can roughly imagine as a tiny arrow pointing up or down relative to some direction. In quantum mechanics, before you measure that spin, the electron is not secretly up or down. It is in a superposition, a mathematically precise combination of both possibilities at once, described by a wave function that encodes the probabilities of each outcome. Now imagine creating a pair of electrons in a way that conserves angular momentum, like two ice skaters pushing off each other so their total spin adds to zero. Quantum mechanics then gives them a joint wave function that says one will be spin up and the other spin down, but it is fundamentally undefined which is which until a measurement happens. The pair is entangled. You cannot assign a definite spin to either electron alone, only the pair as a whole has a well-defined relationship, always opposite, perfectly anti-correlated. Here's the twist. Suppose these electrons drift light years apart. You measure one and find spin up. Instantly, the other one's state is no longer a 50-50 superposition. It must now be spin down if the total is to remain zero, and experiments confirm this correlation every time. The timing is crucial. The measurement results are linked in a way that cannot be explained by any signal traveling between them at or below the speed of light. The statistics of many such measurements violate what are called Bell inequalities, mathematical limits that any theory with only local hidden variables would obey. Einstein hated this. He called it spooky action at a distance, and suspected that quantum mechanics was incomplete, that particles carried pre-existing instructions, hidden variables, deciding every outcome in advance, with no need for instantaneous influence. But starting in the 1960s, John Bell turned this philosophical unease into a testable framework. Decades of increasingly precise experiments with photons, ions, and even superconducting circuits keep giving the same answer. The universe violates Bell's local realism. You cannot explain these correlations with any theory that has both locality, no faster-than-light influences, and realism properties that exist with definite values before measurement. Entanglement doesn't let us send usable messages faster than light, because we still can't control which random outcome any single measurement will produce. But it does reveal that in the quantum realm, separate objects can form a single non-local state, a pattern of correlations spread across space. Our classical intuition that the world is built from independent, localized pieces quietly fails here. And this strange linkage is not just a curiosity. It is the resource behind quantum computers, quantum cryptography, and quantum teleportation, where the full implications of spooky become even more radical.